Hello, good morning students. How do you do? In this class, we will see how the different formulae can be derived and used to find out the velocity in the open channel flow, and then discharge you can calculate using the formula Q is equal to area of cross section of channel multiplied by velocity. There are different formulae developed by different engineers such as Chezz's formula, Manning's formula. Among these two, Manning's formula is more generally used, and it is an empirical formula developed by Manning's Irish engineer in year 1889, whereas Chezz's formula developed in 1775, his duration or tenure between 1718 to 1798. While deriving the equation, he has made many assumptions. We will see. Up to the last class, we have learned uniform flow, non-uniform flow, what is steady flow, unsteady flow, etc. in detail. What is uniform flow? A flow is said to be uniform if its flow characteristics such as depth, h, area of cross section A, velocity v, discharge q, etc. remain constant with respect to distance. As mentioned earlier, the term uniform flow in open channel is understood to mean steady uniform flow. The depth of flow remains constant at all sections in a uniform flow. You can see from this figure, let us consider section 1-1, section 2-2. The depth y or h taken in different books remains same throughout the length of the open channel. What are the assumptions made by Chezz? Or in general, what are the assumptions? 1. Flow is steady and uniform. Channel bottom slope is very small. Channel is prismatic. And energy line will be constant, as V is equal to constant throughout since depth is constant. And therefore, SF is equal to S0 is equal to SW, as Y is constant. SW is the slope of the water surface, S0 is the slope of the bed, SF is the slope of the energy line. The energy line you can see here. Energy line you can see here. This is the energy line, V squared by 2G. Okay. Consider a longitudinal section of an open channel in which the flow is steady and uniform as shown in figure. The forces acting on the free body of water between section 1-1 and section 2-2 in the direction of flow are as follows. 1. The hydrostatic pressure force F1 in the direction of flow, at section 1-1, F2 in the opposite direction of the flow at section 2-2. Component of weight W sin theta acting in the direction of flow, and one more is SF is equal to SW is equal to S0. Slope is remain constant. The frictional force due to air resistance or frictional force due to the friction at the bed of the slope may be considered as very negligible. Pressure forces, that is hydrostatic pressure force, F1 and F2 acting on the two ends of the body. These forces balance each other since the depth of channel remains constant. Okay. The component of weight of the water in the direction of flow, which is W sin theta. Capital W is weight, theta is the slope, which is shown here at the bed with respect to datum line horizontal. That is equal to small w AL sin theta, where A is cross-sectional area, L is the length between the section 1,1 and section 2,2, where W is specific weight of water and theta is the angle of inclination of channel bottom with the horizontal, that is datum line. Third, frictional resistance offered by the sides of the channel, which is given as Fr, which is proportional to AV squared, which implies Fr is proportional to P into L into V squared. Therefore, Fr can be considered equal to small f multiplied by P multiplied by L multiplied by V squared, where P is the wetted perimeter of the channel and F is a non-dimensional factor whose value depends upon the material and nature of flow surface, where F is a non-dimensional factor whose value depends upon the material and the nature of flow surface. As the flow is steady and uniform based on our assumptions, it is neither accelerating nor deaccelerating. The liquid mass is in equilibrium, therefore. The liquid mass is in equilibrium and the frictional resistance to flow equals the weight of liquid mass acting along the line of fluid motion. Therefore, we can write WAL sin theta, WAL sin theta here is equal to small fp multiplied by LV squared. If you rearrange and rewrite, we get V squared. Our aim is to get the value of velocity by Chezz's formula, velocity V in meters per second. Therefore, V squared can be written equal to WAL divided by FPL multiplied by sin theta. Further, if we simplify, we will get value of V is equal to under the root WF, certain components we can take together as it is developed and suggested by Chezz. W by F under the root multiplied by under the root A by P sin theta. But A by P we know it is nothing but hydraulic radius capital R. Sin theta is almost equal to theta because slope is very small, and put C is equal to under the square root W by F, where C is variable which depends on the roughness of the channel surface and is termed as Chezz's constant. That can be found out by using Kutter's formula and Basins formula that we will come across just after 5 minutes. Therefore, velocity V, we can write it as Chezz's constant C multiplied by under the root Rs, where R is the hydraulic radius, S is the bed slope. This is known as Chezz's formula. Therefore, discharge Q can be calculated as Q is equal to AC under the root Rs. Sometimes Chezz's equation can also be written as Q is equal to K multiplied by under the root S, where K is equal to AC multiplied by root R, where K is equal to AC multiplied by root R is called the conveyance of the channel section, and it is a measure of the carrying capacity of the channel. For a channel of constant slope, conveyance is directly proportional to discharge Q. So in this equation, if bed slope is considered to be constant, then conveyance K is directly proportional to Q. Barabar? Further, it may be noted that Chezz's constant is not a dimensionless. Always, what we have come across so far, if we come across the term coefficient, we understand that it is dimensionless quantity. But it is not a dimensionless coefficient, but it has the dimensions as L to the power of half multiplied by T to the power of minus 1. Although Chezz's equation is quite simple, as though the equation is quite simple, the selection of correct value of C is rather difficult. Therefore, we can find out, depending upon the surface of the channel and the bed slope, the value of C using two different equations, as I mentioned earlier, known as Kutter's formula and Basins formula. The Gangulate Kutter formula, one suggested for getting the value of Chezz's constant C, and Basins formula to find out the value of C, which depends on the name of the channel with inside surface, how it is, and value of capital N in case of Kutter formula. What is Kutter formula? It is stated as C is equal to 23 plus 0.00155 plus 1 upon capital N, where N is Kutter's constant. You can see here N is Kutter's constant, whole divided by 1 plus 23 plus 1 plus whole multiplied by 23 plus 0.00155 divided by 1 multiplied by capital N upon root small m, where small m is hydraulic radius. See, at the earlier slide, in the earlier slides, we said R, capital R is hydraulic radius. Here it is taken as m. That's why when you refer different textbooks, R is equivalent to m. Means these two symbols are used for hydraulic radius or hydraulic depth. Okay? N is Kutter's constant, m is hydraulic radius. The value of N, that is Kutter's constant, varying from 0.01. This value varies from 0.01 to 0.15. Next formula, Basins formula. Basins formula. Small k is Basins constant, small m, as it was before, hydraulic radius. Formula for C to evaluate the value of C is equal to 157.6 divided by 1.81 plus k upon under the root small m. Here k is Basins constant, that depending upon the nature of channel inside surface, and value of k ranging from 0.11 to 3.17 depending upon the nature of channel inside the surface. In the previous case, Kutter's formula, very smooth surface of glass, plastic or brass, smooth surface of concrete, etc. In case of Basins formula also, smooth cemented or planed wood, brick or concrete or unplanned wood, etc. The value varies 0.11, 0.21, 0.83, etc. up to maximum value of 3.17. Next, Manning's formula. In 1889, an Irish engineer, Robert Manning, presented a formula according to which the mean velocity V of uniform flow in a channel is expressed in terms of a coefficient of roughness small n called Manning's constant, hydraulic radius R, and channel bottom slope S. The Manning's formula expressed in SI or metric unit is written as V is equal to 1 upon N S to the power of half multiplied by R to the power of 2/3. If it is equated with the Chezz's equation, because from Chezz equation also we know V is equal to C under the root Rs. That can be equated to 1 over n s to the power of half r to the power of 2 by 3. After simplifying this equation, we get the value of C in terms of n also, that is Manning's constant. C is equal to 1 upon small n multiplied by r to the power of 1 by 6. Value of n here, Manning's constant, are also similar what we have discussed in Kutter formula, right? Separately we need not have to take once again that formula. We know though that formula. What is that formula? If you want, you can refresh. Kutter formula, C is equal to 23 plus 0.00155 plus 1 upon n divided by 1 plus 23, 1 plus whole multiplied by 23 plus 0.00155 divided by I multiplied by capital N upon under the root small m. Here the capital N is Kutter's constant. The same constant is taken as Manning's constant, which depends on the nature of the channel and the slope. Value of n is the constant or coefficient. Is it right? References: P.N. Modi and S.M. Seth, Hydraulics and Fluid Mechanics, including hydraulic machines in SI units. Standard Book House, unit of Royson's Publications Private Limited, publication house. Second book, K. Subramania, Flow in Open Channels, Tata McGraw-Hill Publishing Company Limited, publication house. Third one, R.K. Rajput, a textbook of fluid mechanics and hydraulic machines in SI units, Chezz and Company Limited, publication house. Lastly, R.K. Bansal, this is specially more useful for numerical problems. Many good numerical problems have been solved by him. A textbook of fluid mechanics and hydraulic machines in SI units, Lakshmi Publications, Private Limited, publication house. Thank you for watching. At least please practice soon after this, after 1 hour or 2 hours, whenever you find leisure time, practice these two formulae how to derive. Very simple. Only matter is patience. So with patience, please practice twice at least by referring to the literature. Definitely you will be able to derive and understand the concept behind these two formulae, Chezz's formula and Manning's formula. We will stop here for today's class. Okay, thank you.